So thanks for joining again my lecture series on course on optics. And now we are starting our journey on towards or through the last chapter regarding geometrical optics. And before I get started with the actual main message of the video, which would be the basic definitions, basically regarding the terminology that we will be using in what follows in the chapter, I would like to go through the other bits and pieces that we will be going through in this chapter, so that you know what you're waiting for, and hopefully you get a better understanding of the kind of big picture that we have in our last series of lectures. So I will be first starting with the basic definitions here at the point of this video. And then after that, I will speak about refraction taking place at a spherical surface, as the name of this section suggests. We can now, after this lecture, we can understand how refraction takes place on a spherical surface. So we do the bits and pieces of mathematics to understand what happens for a ray of light. And after that, we can combine two spherical surfaces together to understand how a thin lens essentially behaves. So basically, some kind of optical glass or transparent medium which has two spherical surfaces of given radius, and then we can form actually lenses, and we can understand how they behave. And now, once we know how a lens is being formed, we can also form a lens equation, and we can understand how images are being formed. So we can really image an object into an image, and in here in this chapter we will be going through that mathematics. And then once we know about everything regarding image formation using a single thin lens, in section 10.5 we go into a combination of lenses. So we generalize our treatment to the possible scenarios where we actually have many lenses, and then we're using them to image our objects. And at this point I would like to emphasize that our treatment on geometrical optics is really heavily focused on imaging of things. And this is, although it's a big part of optics, imaging optics, and related terminology and bits and pieces of information, that's of course not all, but there's also a huge portion of optics and photonics that deals with non-imaging optics. So for example, lighting of things is a big piece of a big example of that kind of physics and optics taking place. So for example, when it gets dark, we light up our rooms with using lighting, and there of course we're not most of the time wanting to image our light sources inside the room, but rather we want to have a kind of diffuse like a homogeneous illumination into our spaces of interest. And then in the lecture 10.6 I will be speaking about apertures and stops. So essentially they would be instruments, components that allow to control amount of light propagating through our lens system. And these, of course, start to become especially important when we would go beyond the paraxial approximation. So when we would have light rays that are propagating at angles that are very large compared to the kind of rays that are propagating mostly along the optical axis. So essentially, when we have rays of light going through our lens system, imaging system, or optical instrumentation in general, where rays of light propagate also with other directions than along the optical axis, then it's the apertures and stops that start to be more important. So essentially, when paraxial approximation fails and when aberrations start kicking in our treatment. But we don't really deal with optical aberrations in this course. So if you're interested, please join us in the follow-up course. Optical systems and beam propagation, for example, is a good course with that respect. And there we will see more what the apertures and stops as components can actually do. And then we will speak about mirrors, we will speak about prisms. Especially with mirrors, we try to understand how they can be used in terms of imaging optics. And then with prisms, the focus here will be also on the kind of point that you can use prisms either as a helping tool to, for example, flip the orientation of your image. So for example, in binoculars, you can use prisms, but also prisms can be used as diffractive optical components so that we can disperse different frequency colors to propagate in different directions. So there's these two different functionalities that we have with prisms. And then we will speak about the human eye, especially from the optical point of view, how it behaves, what are the main tools or main building blocks in the human eye from the optical point of view, so that how rays of light are propagating through the human eye and then are being guided into the detector and how an image is being formed there. So essentially, after that lecture, we can understand how the human eye behaves as an imaging instrument. And then we can also appreciate what kind of limitations we may have with our human eyes, which is, of course, quite interesting from the kind of general point of view, but also when we want to understand what kind of optical instrumentations we could use, where we are actually using them by just using human eyes as the detecting instrument. So, for example, like a telescope, a handheld telescopes, and binoculars and such. And then we will speak about magnifying glasses in 10.10, and I would see this as a prelude to really on our second to last chapter section on microscopes. So basically, we want to understand how we can form a magnified image using a single bit of a glass as a lens. And then we will speak about eyepiece as an optical component. So essentially that's also known as an ocular lens. And that is also useful when we want to build a microscope or binoculars, so to speak, so that how we can change the magnification of our imaging optics by having several lenses. And then finally, ultimately, we will be ending by just speaking about a few configurations of telescopes that exist or have existed out there. So these would be the kind of historical telescope configurations. And these are, of course, not the ones that are more modern and more conventionally currently used to actually as a telescope. But at least it provides us a kind of culmination to understand how we can build optical instrumentation by just putting lenses together, and that's the main thing I wanted to point out in those last few lectures we have regarding microscopes and telescopes. So this will be the curriculum of this chapter, so what we will be listening in the next 1 week or two. So I hope you will enjoy the ride as you have so far, and I will now start with the actual first lecture regarding the basic definitions. So here I will start the first lecture. So, like I already mentioned in the introduction to the whole chapter, like a huge chunk of classical optics really deals with non-imaging optics. So that essentially, for example, means lighting. So when we are thinking about such problems that when it gets dark and we use our vision to guide ourselves into places, we need some kind of lighting. And that might either be inside rooms, or if you're driving the car, we need to maybe have traffic lights and street lights that are helping us out. And in addition, there's also lighting taking place inside the car. So I mean the driving lights, so that we can see the street ahead of us. So there's a lot of optics taking place where we do not really need to image things, but rather we would just want to illuminate things. And this is actually not a trivial task, and there's actually quite a lot of designing complications on the way when we want to have a kind of cute diffuse lighting that is uniformly lighting things that we want. So this is not entirely a trivial thing. But from our course point of view, we are not dealing with non-imaging optics, but rather we are focusing on imaging optics. And this is my main point that we will be looking at theoretically here. So we are looking at optical systems that have been shown in that figure. So we have an object space, and we have some kind of object location or even a non-point like object, and we want to image that into the image space and into a point P. And then this is basically our problem statement that we want to understand and look at during these lectures and this chapter. So we have an object, we have a source point S, and how that is being imaged into an image point P. This is our main problem statement. And either we can illuminate the object, and that way light is being scattered by the object point, and then we are illuminating that scattered light into the image point, or the object point in itself can also radiate light. So it could be, for example, a fluorescent molecule. That would be many times a relevant scenario when we are looking at fluorescent microscopes. But in terms of other types of imaging, many times it's actually the scattered light that is the relevant piece of light that actually dictates how we are imaging things. So object scatters light, and we are imaging that scattered light, and using that we can actually form an image of the object. And when we're looking at what is the function of our imaging instrument, it's basically to collect the scattered or emitted light, and most of the time I would say the scattered light, and then somehow we want to form an image using the scattered or emitted light of the object. And this is our main function. We want to somehow image something, maybe even change the magnification so that we can see, for example, small things, or we could see far away things by just having a greater magnification. So these would be the kind of answers we would want to be answering. And terminology-wise, when we have an object where we have a source point, that will be inside the object space, and many of the times in the drawings, that would be on the left-hand side of the lens, and then the image is being formed into the image space. This is a piece of terminology. Maybe it's good for you to remember, but at least you should remember the object and image as a piece of terminology here. Now, another thing we should remember is that we may have a system that is called stigmatic, and a system is stigmatic from the point of view of imaging when there is a perfect correspondence between the object and the image points. So basically, this means that when a point S, our object point, is imaged into a point P, and this is still a point, so that the image point is not blurring of a point S, but rather it's still a sharp singular point that we see in the image space. And in this case, when we are looking at the behavior or in the kind of imaging quality of our instrument, we could really reverse the behavior and nothing would really change. So in this case, the object point P would also be imaged into a point S, and so that the S source point and the P points, they are essentially conjugate points. So let me highlight this, that essentially we could imagine what happens, that this would be our object point, and we are imaging that into a single image space point here. And then if this is perfectly stigmatic, so that there's only a single image point here, we could as well just reverse the direction of light, and then we could similarly have a image point P being imaged into an object point S here. And this is as long as we have a perfectly stigmatic system, so that there's no kind of blurring out of the imaging processes. This, of course, is something that never takes place in actual nature, which is basically due to the wave nature of light. And this, as we know, gives rise to diffraction effects, and then this gives rise to the fact that there's always some kind of blurring out of image point when we're actually using a realistic or a real imaging system to perform some kind of imaging. So we cannot really realize a perfectly stigmatic systems physically. We can only manage with what we call a diffraction limited system. And that means that essentially we can imagine that it behaves ideally, but in the end we know that if we would really want to calculate what this would be, like how a point like this would be, we would need to take into account the diffraction of the system. So how much of light is being diffracted, and thus how much it actually being blurred out during the imaging process. So this is the best case scenario we can actually realize in a physical system. So we can achieve a diffraction limited system, but we cannot achieve a better system. And now we are in this chapter in using the framework of geometrical optics. And here we are really totally neglecting the fact that light is behaving like a wave-like quantity. So we essentially assume that the wavelength of our incident light of interest that is propagating through the system and causing objects to be imaged, that the wavelength is approaching zero. And what this means is that we can basically neglect diffraction effects, and then we can really just do our treatment of propagation of light through the system by just using the concepts of rays, as we have already mentioned in the previous chapters. And this is quite nice because this really helps our understanding and treatment of the system. So we can really consider then a scenario that we have an object plane and then points are being imaged nicely into points in the image space and not, for example, a blurred locations, distributions. And from the geometrical point of view, when we say that a system would be stigmatic, basically it corresponds to a system where it's behaving diffraction limited. So this is the best we can achieve from the physical point of view. And if somebody would be saying in geometrical optics that we have a stigmatic system, or there would be, for example, a homework problem that consider a stigmatic system, then you would know that, okay, this is the kind of best case scenario, and we only are limited by diffraction. And most of the time we do not need to consider those when we're looking at problems related with geometrical optics. So we don't really need to do calculations where we would be estimating how much of things would be blurred out by diffraction of light. So here in geometrical optics, point object S is basically forming an image point. And of course, ideally, the imaging process gives us a point-like image. But in reality, of course, it would be slightly blurred due to diffraction. But usually we are not dealing with that kind of picture, but rather we are considering this kind of scenario. So this is usually what we think of in the geometrical optics picture when we are speaking of stigmatic systems. So we neglect the diffraction in a way that we just draw a point-like image into here, although we know that in real case there would be some kind of diffraction blurring our images. Of course, when we would be moving beyond so-called paraxial approximation, I will be introducing that shortly in the next lecture. Of course, imaging systems are in practice also imperfect, also even in the point of view of geometrical optics. And what this means is that even in this framework, object point S can be imaged into a blurry image point B. And this is in fact most of the time what actually happens when we are dealing with real imaging using real lenses. So for example, spherical lenses, they can be easily manufactured, they are relatively cheap, and we can use them to image things. It's nice, but if we have a lens power increasing so that the curvature of the spherical surface increases or the refractive index profile increases, then we are necessarily also introducing different kinds of aberrations into the imaging. And then a single point will not be imaged nicely anymore. So this is the kind of real problem at hand when we are moving into real imaging systems. And what basically is the kind of limiting factor here? It will be the optical aberrations. And here, I guess in this chapter at the end, and I think in a homework, I will be giving some kind of exercise for you to figure out what gives rise to aberrations physically, but we do not deal with them in a systematic manner, and we do not deal with the mathematics associated with aberrations. There would be, of course, a nice bit of theory aberration regarding aberrations, so basically aberration theory, where we would be extending our approach, but that is beyond our introductory course. And of course, if you're interested in learning more of those, I really recommend you to go into our follow-up courses, where we will be really focusing in image formation and what kind of different aberrations exist, how they are being affected by the wavelength of incident light, possibly, and then how images are being blurred or distorted due to lens aberrations, and how we can tackle these aberrations. And this is actually a big thing in terms of designing optical components and instrumentation. So this is what will happen when we improve our system and treatment of our system, and that would be highlighted in the B. Okay, this is what would be happening in a real system. Images get blurry, but here we are rather much more interested in kind of scenario A, where we are totally neglecting possible lens aberrations, image aberrations. But of course we know, and you should be aware of this fact that we actually do have aberrations present in all imaging systems if you just look carefully enough. And then the final things I like to mention here, when we're looking at the imaging, It's also important to know that there's actually two different kinds of images. So there's a so-called real image and also a so-called virtual image that can be formed. And what are the main, in simplicity, the kind of differences here is that if you're considering a real image point, it really like forms into an image-based location where the incident rays really physically cross each other. So if we are, for example, drawing lines, how a lens is being refracting different rays, or we are doing actual like a ray tracing using a software, we would actually be seeing that these kind of rays of light would be actually like focusing down into a single spot, and we would know that there's actually a physical image being formed. And the kind of difference between a real image and a virtual image is that when we have a virtual image point, the rays only seem to cross. So basically they seem kind of originate from that one single location, but they do not actually physically cross there. And here in practice, these locations of virtual images, they are located in the object space. Or for example, in the case of mirrors, if you have an image being formed that is kind of beyond the mirror reflecting surface, you know that it's a mirror, no light will be transmitted through the mirror, and nevertheless it seems to be that my image is actually being formed beyond the mirror. You know right away that this has to be a virtual image, that this is not a physical image that can be formed there. So this is the kind of like things like you should be familiar with, and of course we will be speaking more about these points when you're actually going into the imaging using lenses and mirrors. But at least it's good for you to be familiar with this kind of basic terminology before we are actually there to kind of be able to kind of already start grasping of the kind of main things and nuances regarding our curriculum. So this was my first lecture. I thank you for joining me and listening all the way through. And I will be next speaking about the actual refraction taking place at a spherical surface. So basically I will be starting our journey to understand how lenses are behaving as a imaging instrumentation. So I thank you for your time and patience, and please join me shortly with the next video. Thanks and bye-bye.